Okay, so 2 units down, and we are jumping into the third unit. So our third unit is all about solids, liquids, and gases. So we're first going to start by understanding what changes states of matter. We can have different things at the same temperature, and yet they'll have different states. So let's talk about what that is. And that is intermolecular forces. So we're going to jump into our PowerPoint for intermolecular forces. And that should show up here in just a second. Okay, so here we are. And we're going to talk about intermolecular forces. So we start with this image of a gecko because he uses actually intermolecular forces to climb different objects, including the glass. So first, a quick review of what intermolecular forces are. So these are the forces between molecules that hold molecules together. This is not the forces inside the molecule. Those are called bonds, and those are intramolecular forces. So these are the forces of attraction between molecules or between molecules and ions. And so we're going to talk about several different intermolecular forces today. We're going to talk about ion-dipole forces. We're going to talk about dipole-dipole forces. We're going to talk about London dispersion forces, and we're going to talk about hydrogen bonding. But first, let's talk about what intermolecular forces are. So these are those attractions between molecules. They are not nearly as strong as the intramolecular attractions that hold compounds together. So these are not nearly as strong as bonds. They are, however, strong enough to control physical properties like boiling and melting points, vapor pressures, viscosities, and many other characteristics like capillary action. As a group, we can refer to all of the intermolecular forces as van der Waals forces. So that's an older term, but you will still sometimes run across it. So we've already talked about what these are. So let's rank these in order of strength. So covalent bonds are intramolecular forces, not intermolecular forces. So I just have them on here so you have a point of reference for strength. So hydrogen bonding is generally considered to be the strongest intermolecular force, and it only has a bond energy of 12 to 16 kilocalories per mole. So that is not very strong, especially when you compare it to the covalent bonds, which are many times stronger than they are. The next strongest one is dipole-dipole interactions, and those are even smaller, a half a kilocalorie per mole to 2 kilocalories per mole. And then the weakest of the intermolecular forces are what we call London dispersion forces, and those are generally less than 1 kilocalorie per mole. So let's talk about these types of intermolecular forces. The first one is what we call hydrogen bonding. So hydrogen bonding is the type of interaction. Please remember it is not a bond despite its name. So it is the type of interaction that occurs when hydrogen in a molecule is bonded. Now we are talking about a bond to either nitrogen, oxygen, or fluorine. Now, because nitrogen, oxygen, and fluorine are so electronegative, then that means that they pull very, very hard on the electrons that they are sharing with hydrogen, which makes the hydrogen essentially a bare proton. So it can then be attracted to the electronegative portion of a neighboring atom or a neighboring molecule. That can be the same. So here we have 2 water molecules, and we have this hydrogen that is bonded to the oxygen being attracted to the electronegative oxygen on the nearby molecule of water. We can also have this between 2 different molecules. So again, here we have hydrogen bonded to oxygen, and now it is being attracted to the electronegative nitrogen of a nearby ammonia molecule. So that's what we call a hydrogen bond. Please, please, please remember that a hydrogen bond is not a bond, it is an intermolecular force. They only occur when the hydrogen in a molecule is bonded to either nitrogen or oxygen or fluorine. This attraction right here is what we call the hydrogen bond. It happens because of that high electronegativity. So we essentially have a bare hydrogen nucleus, which is then attracted to other electronegative atoms. Hydrogen bonding is responsible for a lot of things that we see around us. Hydrogen bonding is responsible for the structure of snowflakes. It is responsible for the fact that ice is less dense than water. Hydrogen bonding is incredibly important in biology. In DNA, you guys know that T bonds only to A, and that's because thymine hydrogen bonds to adenine. And there are two spots where it can do that. Here, where you have a hydrogen bonded to a nitrogen, and again, here where we have a hydrogen bonded to a nitrogen, and then it is attracted to either the oxygen or the nitrogen on the other molecule. Cytosine bonds to guanine, hydrogen bonds to guanine. But this time there are three, and this is why cytosine bonds to guanine and thymine hydrogen bonds to adenine, and they don't mix. Okay, so that's hydrogen bonding. Let's talk about some dipole forces. So we talked about dipole-dipole. Hydrogen bonding is a specific type of dipole-dipole. So and then we also have ion-dipole interactions. And these are actually stronger than hydrogen bonding. So ion-dipole interactions are where we have an ion being attracted to a polar molecule or a dipole. These forces are very strong. This is why ionic compounds dissolve in polar solvents. So the strength of the attraction between an ion and a water molecule is what makes ionic compounds dissolve in water. Next type of dipole interaction is what we call a dipole-dipole interaction. So now we're talking about two of the same or two molecules that are both dipoles. And because they have permanent dipoles, they're polar molecules, they are attracted to each other. So positive end attracted to negative end. And this is a relatively strong intermolecular force, weaker than hydrogen bonding, but still relatively strong. And then the next type of interaction that we're going to talk about is what we call a dipole-induced dipole. So a dipole-induced dipole is when a polar molecule gets near a non-polar molecule. And when it does that, the negative end of this particular molecule, which is what's approaching it, is actually going to push the electrons in the nonpolar molecule to the other end of the nonpolar molecule. And this creates a temporary dipole. And this causes an attraction between the permanent dipole and what we call an induced dipole or a temporary dipole. And this is why some nonpolar substances like oxygen do dissolve in water, because water is such a strong dipole that it can actually dissolve nonpolar substances. So, and we know that fish are very grateful that oxygen is soluble in water. Otherwise, they would not be able to just keep swimming. Okay, so our weakest type of intermolecular force is what we call London dispersion forces, named for Fritz London, not for the city. So London dispersion forces are the only forces that nonpolar molecules feel towards other nonpolar molecules or exert on other nonpolar molecules. We can call these London forces, dispersion forces, or dispersion interaction forces. Please do not use the term van der Waals forces for London dispersion forces, because van der Waals forces applies to all of the intermolecular forces. So how do these work? So we're going to use helium as our example. We know that helium is normally a gas, but if we put it under enough pressure or get it cold enough, then it actually can become a liquid. And in order for it to do that, it has to be experiencing some intermolecular attractions. Normally, the two electrons in helium spend time kind of in opposite sides of their orbital. But occasionally they both wind up on the same side. And when this happens, we wind up with a temporary dipole because we have the two negative electrons on one side and nothing on the other to balance the positive charge. So we get a temporary dipole, as we see illustrated here. And that temporary dipole, when it gets near another nonpolar molecule, is going to induce a dipole in the other nonpolar molecule. And we're going to wind up with a temporary dipole and an induced temporary dipole, and we're going to have an attractive force. Now, these form quickly, they go away quickly. These are not strong forces. But it's important to recognize that London dispersion forces are present in all molecules, whether they're polar or nonpolar. So a polar molecule will experience London dispersion forces and dipole-dipole forces, could potentially experience ion-dipole forces. A molecule that experiences hydrogen bonding will also experience dipole-dipole and London dispersion forces. So generally speaking, as you move up, you experience all the weaker ones plus the highest one. All right, so let's talk about some of the things that can make our London dispersion forces stronger or weaker. We know that they're the weakest of the intermolecular attractions, but can we find ways to make them stronger, or are there things that make them stronger? So London dispersion forces depend on this polarizability, this ability of the electron cloud to become distorted and have a partial positive and a partial negative charge. Therefore, the more polarizable the molecule is, the stronger its London dispersion forces are going to be. So what are some of the things that can make a molecule more polarizable? One of the things that can make a molecule more polarizable is the shape of the molecule. Long, skinny molecules are more polarizable, so they have stronger dispersion forces than short, fat ones because we have bigger surface area. Okay, the biggest thing that affects London forces is the number of electrons. The more electrons there are in the electron cloud, the more polarizable that electron cloud becomes. So what that means is that we can use atomic mass or molecular weight as a shortcut to tell us how many electrons there are. And therefore, the more massive it is, the more electrons it has, the more polarizable it will be. And so you can always look at molar mass to compare two nonpolar molecules and know which one is going to have the stronger London dispersion forces. Okay, so why does all this matter? We care about intermolecular forces because they tell us about the way that the molecules interact with one another. So how can we assess this, and how can we see this, and how can we talk about it? So we care about it because when we talk about states of matter, so solid, liquid, or gas, the state that a substance is in at a given temperature and pressure depends on two things, and those two things are working against each other. One is the kinetic energy of the particles. The faster they're moving, the more likely they are to be able to get away from each other. And then the other thing it depends on is the strength of the attractions between the particles. And now we're talking about intermolecular forces. So the state of the substance depends on which of these two forces is stronger. The stronger the intermolecular forces, the higher the substance's melting point and boiling point is going to be. So if we look at our dipole-dipole interactions, we can see that the more polar the molecule is, the higher its boiling point becomes. So the more polar it is, the more likely it is to be a solid at room temperature. So if we look at fluorine versus hydrogen fluoride, the boiling point of fluorine, F2, is negative 188.14 degrees Celsius, but the boiling point of hydrogen fluoride is 19.5 degrees Celsius. So hydrogen fluoride experiences much stronger attractive forces, right? In fact, not just dipole-dipole interactions, but hydrogen bonding because we have hydrogen bonded to fluorine. If we look at London forces or London dispersion forces, the bigger the hydrocarbon gets, and therefore the more electrons that it has and the more polarizable it is, the higher the boiling point of those hydrocarbons, which are nonpolar molecules. So again, the stronger the London dispersion force, the higher the boiling point. Okay, we already talked about that. Okay, one more. We're going to talk about this particular diagram, which shows us boiling point as a measurement of intermolecular attractive forces. And what you can see here is that we are showing different groups. So the carbon group, the nitrogen group, the halogens, and the oxygen group. And we're showing how as their mass increases, that these have stronger intermolecular forces, which means they have higher boiling points. This group right here is a huge exception. And the reason that this group right here is a huge exception is that when hydrogen is bonded to oxygen or nitrogen or fluorine, it has hydrogen bonding. So it has abnormally high attractive forces, and therefore it has high boiling points. Okay, one more thing that we'll use to talk about intermolecular force strength is this idea of equilibrium vapor pressure. And you might remember from our discussions about equilibrium that in any liquid, some of the molecules are constantly escaping the liquid, they're evaporating. If that liquid's in a closed container, the number of molecules escaping, evaporating, will be equal to the number of molecules condensing. So if we take a water bottle and we take a look at it, I don't know if you guys can see this, you can see that there's some condensation here on the side of the water bottle because as it sits, water evaporates and then it recondenses on the surface of the water bottle. And so that's equilibrium vapor pressure. Now those gas molecules, before they recondense, they exert a pressure. And that pressure is what we call equilibrium vapor pressure. So the more difficult it is for a liquid to evaporate, the more difficult it is for those molecules to escape, the lower the equilibrium vapor pressure is going to be because you're going to have fewer molecules of gas. So that means that liquids with higher intermolecular forces are going to have lower evaporation equilibrium vapor pressure. Liquids with lower intermolecular forces will have higher equilibrium vapor pressure. Okay, so just a few practice exercises and then we'll be done. So if we look at bromine, neon, hydrogen chloride, hydrogen bromide, and nitrogen, which is likely to have the largest intermolecular forces? So largest intermolecular forces, well, this is going to be nonpolar. This is going to be nonpolar. These two are polar, and this is going to be nonpolar. So we know it has to be one of these two, either the hydrogen chloride or the hydrogen bromide. And since chlorine is more polar or more electronegative, this is going to be a more polar molecule. So it's going to experience larger dipole-dipole forces. If we look at London dispersion forces, then we're looking at bromine, neon, and nitrogen. And we're looking for the one with the greatest mass and the greatest number of electrons. And so that's going to be bromine. So bromine is going to have the largest London dispersion forces. In which of these substances could we have significant hydrogen bonding? Methylene chloride. Well, in methylene chloride, I have hydrogen, but it's bonded to carbon, so that can't have hydrogen bonding. Phosphine, where I have hydrogen, but it's bonded to phosphorus, that's not nitrogen, oxygen, or fluorine, so no hydrogen bonding there. Hydrogen peroxide, okay, now I have oxygen bonded to hydrogen, so it's certainly possible there. Or acetone. Acetone is CH3COCH3. Although I have hydrogens here, they're bonded to carbon, so no hydrogen bonding here. So it has to be our hydrogen peroxide. And the last one, we are looking at intermolecular attractions present in these three substances And we want to know which one will have the highest boiling point. So we have ethane, we have ethanol, oh, nope, sorry, we have methanol, and we have ethanol. Okay, so ethane here, CH3, is a completely non-polar substance, so it's only going to have London dispersion forces. CH3OH, the methanol, and CH3CH2OH both are going to have hydrogen bonding because they have the hydrogen attached to an oxygen. So these two, methanol and ethanol, are both going to have hydrogen bonding, dipole-dipole, and London dispersion forces. Now, if we want to know which of these two will have the highest boiling point, because it's definitely going to be one of these two because they have hydrogen bonding. Now, the amount of hydrogen bonding between these two is the same because we don't have any more hydrogen bonded to electronegative atoms on either one of them. And so now it's going to come down to the fact that they also both have London dispersion forces. And since this is a larger molecule, it's going to have larger London dispersion forces, so it will have the highest boiling point. So hopefully that refresher of intermolecular forces helps you remember what we learned in honors chemistry. As always, let me know if you have any questions. Thanks.